Hello everybody. In this video we are going to be covering some examples of orientability. So the first example is that of a smooth non-singular surface. And so we define this in part 2. And so I'll recap basically the definition. So MK, I'll just call it MK, is a k-dimensional surface, which is defined by what's the word I'm looking for? There's a better word, but I'll just say a set of equations, system, that's the word I was looking for. A system of equations, n minus k equations, in terms of the variable x, which is an Rn, so that's why I'm writing it with this little vector notation. So n minus k equations like this, where the rank of the matrix formed by the partial derivatives is maximal, which is going to be n minus k, because this is an n minus k by n matrix. So n minus k is the highest rank it can achieve. So this is the definition of a smooth non-singular surface. It's a k-dimensional surface in Rn. And so we are going to prove that this is orientable. And we're going to use the second definition of orientability, which is that of choosing a frame. So we want to show that we can choose we want to have a continuous choice of orientation class on M. Now, let's just say we arbitrarily choose, how do I say this? So choose orientation class, or orientation classes at each x and m, right? Or let's just say we assign to each x some frame, tx, or tau x. So let's imagine this surface here. Let's say we're in R2, and let's say our surface is a circle. Because this is defined by the equation x1 squared plus x2 squared equals, well, technically minus 1 equals 0. So this is our f1 of x. So at each point we're choosing a frame for the tangent space, which is just, this line R. And so we're not necessarily choosing this to be continuous, right? We're just choosing an orientation class at each point, arbitrarily. Now, we want to look at this frame, tau hat, which is the frame that we get by adjoining tau with the gradient vectors of the functions which define M. So, like in this case, right, the gradient of f1 is gonna be The first component is going to be, if we take a derivative with respect to x1, we'll get 2x1. And then the second component, if we take a derivative with respect to x2, we'll get 2x2. So if we look at this, right, at each point, the gradient is essentially going to be pointing, it's going to be pointing in this direction. It's going to have double the length though, because of this 2. But the point, the thing to notice here is that it's going to be perpendicular to the tangent space, or in particular perpendicular to the surface, but perpendicular to the tangent space is more well defined. So essentially that's how we can adjoin these two things, because tau represents vectors for the tangent space of the manifold, and then all these gradient vectors are going to be orthogonal. So this is tangent to mk, and the gradients are going to be orthogonal to mk, which is a standard fact of gradient vectors, like for multivariable calculus. And the important thing to note here is that we know the tau are linearly independent, because that's part of, they're a basis for a tangent space, so they have to be linearly independent. And these gradient vectors are going to be linearly independent because of this rank condition, right? This matrix is, this is the matrix that we get by putting the gradient vectors up against each other, right? So we have n minus k gradient vectors, and we're saying that this matrix has rank n minus k. If this has rank n minus k, then that implies that the gradients are linearly independent. Because the rank essentially is the dimensionality of these vectors, right? And since it's a full rank, that means they're linearly independent. And so that's just a standard fact from linear algebra. So since these are linearly independent, and these are linearly independent, and these come from a tangent space, and these come from the orthogonal space, if we put these all together, this is going to be linearly independent. And so tau hat is a well-defined basis for Rn. So this is, well, technically it's a frame for Rn. Okay. And again, we're just choosing these taus at each point, right? But we want to be able to show that we can choose it continuously. And essentially what we do is choose, right? We have an infinite selection of tau, and all we'd have to do, we know tau hat has two possible orientation classes. So let's just say that tau hat is in the same orientation class as the standard orientation on Rn. Well, this standard orientation is clearly continuous amongst R2, and so if we restrict to our surface, it's going to be continuous along that surface. So we just choose tau such that tau hat is in the same orientation class as the orientation on Rn. This defines an orientation on M. So essentially, M, since it's a surface in Rn, you can think of this as M is inheriting its orientation from Rn. So that's one way to think about it. All right, now let's consider an example of something that's non-orientable. And this is something you may have seen before. It's called the Mobius strip. So let me try my best to illustrate this. So the Mobius strip is what happens if you take a rectangular strip of paper, and so if we have this rectangular piece of paper here, now if we folded it, if we took this side and glued it to this side, we would get a cylinder. If we instead applied a half twist, so that this point is being sent to this point, so we twisted it like so, then that would make a Mobius strip. Mobius strip. And the Mobius strip is a manifold. It's a two-dimensional manifold, right? Because locally it looks like R2. And it is non-orientable. So let's show why that is. And it's easier to visualize in this drawing here. So I'm going to get rid of this line. Okay. All right. So let's say we pick a point here. And let's say this is our frame. 1, 2, right? This is just a standard frame. And if we move this along here, right? Okay. It's going to be the same, right? We're just moving along continuously. And now when we pass through here, what happens is that since 2 is pointing in this direction, well, points up here are being sent to points down here. So when this point passes here, the orientation frame is going to flip, because this 2 that's pointing upwards is going to be sent downwards. But the 1, this direction doesn't change. This is an opposite orientation. And so what we've done is we've transported this point, this frame, continuously, and we can move this now over here, and we've gotten a different orientation. So this means that you can't define an orientation on the manifold. And so if this explanation doesn't make sense, I've got a visual pulled up here. So here you can see this point is going around, right? And it's always traveling in the same direction along this green circle, right? And that's similar to how in this picture, right, the one direction never changed. But here, if you focus on, let's say, where my cursor is, actually I don't know if my cursor shows up in the recording, but essentially look at the green line passing through the purple point. Maybe if I zoom in, you can see it better. But if you look at the line, you'll see that at one point it will be facing outward, and then when it makes a loop, it's now facing inward. And so that's that's basically the same thing, right? It's making a loop, but the vertical direction is changing. All right, so that is an example of a non-orientable manifold. Now what we are going to do is prove that the real projective space, where n is odd, is orientable. And this is going to be a really nitty-gritty proof. So if you made it to this point in the video, there isn't really much to learn here other than to see how Really, this is a good exercise for getting used to Jacobians and transition functions and stuff like that. But other than that, there's not a lot of intuition to gain from this proof. So yeah, that's just a warning. If you're at this point in the video, that this is going to be a lot of symbols. So anyway, what we're going to do is use the first definition. So we're going to define coordinates on Rpn and show that all of the Jacobians of the transition functions are going to be positive. So I think I mentioned briefly that the charts for Rpn are the essentially hyperplanes in, and remember Rpn comes from Rn plus 1. And so in this space we use y to represent the coordinates in Euclidean space, and then we'll use x to represent the points in the projective space. So the chart U0 is going to be all the points where y0 is not 0. Similarly, the chart UN is going to be all the points where yn is not equal to 0. So what we do is on a chart UQ, so this is where yq is not equal to 0, we define local coordinates xq, I, and here's how we'll define them. Let's see, we start at x1q is going to be equal to y0 over yq. And remember, in UQ, YQ is never equal to 0, so we can safely divide by YQ. Similarly, X2Q is going to be Y1 over YQ, and we're going to continue in this fashion until we hit XQ minus 1. Actually, not XQ, XQ. So here we get that. Now, when we go to YQ plus, XQ plus 1, if we continued in this fashion, we would get YQ over YQ, but that's just 1. That doesn't tell us anything, so we can disregard that part and skip to YQ plus 1 over YQ. And then similarly, we just continue on. Like that. Oh, and so that's the standard definition, but for this proof, we are going to be adding negatives to this part. So these ones are going to have negatives in front. And so we can see that we have n coordinates, right? So this is an n-dimensional manifold. And when I said this comes from Rn plus 1, that's because Rpn is, remember, it's a sort of quotient space of Rn plus 1. Well, technically Rn plus 1 minus 0, because we exclude the origin. It's a quotient space of that. Or you can consider this to be Sn plus 1. Or Sn, sorry. Okay, so this is how we've defined our coordinates on UQ. So now, let's look at for P, basically for each P, like 1 through n, the value xpp, right, is just going to be yp minus 1 over yp. Now suppose, there's more work to do here. This is going to be -1 over negative yp over yp minus 1. And now yp over yp minus 1 is, if we look at this, essentially if we use this thing here, we can see that this is going to be xp p minus 1. So basically what we've done is we took xpp and rewrote it in terms of xp p minus 1. Next, we're going to assume that q is some number less than p. Then xqp is going to be yq minus 1 over yp. And then we essentially normalize. So here what we're doing is we're working on up intersect up minus 1, which is not empty, right? This is just the space where yp is not equal to 0 and yp minus 1 is not equal to 0. So here we normalize like so, yp over yp minus 1, and sorry, this negative should go out here. So yq minus 1 over yp minus 1, since q is less than p, q minus 1 will be less than p minus 1. So this is going to be xq p minus 1, and then this number is going to be xp p minus 1. Oops. Okay. Now we're going to assume that q is greater than p. And my drawing is messing up. Then xqp is going to be yq over yp, which is, or sorry, negative yq over yp. And then we can normalize in the same way. And then this is going to be negative yq over yp minus 1 is going to be xq p minus 1. Since q is greater than p, we know q will be greater than p minus 1. So that's why this is there. And so here we see that no matter what, if q is not equal to p, then xqp will equal negative xq p minus 1 over xp p minus 1. All right. Now, we are going to let J be the Jacobian for the transition between the p minus 1 coordinates to the p coordinates. In other words, it's going to be the matrix dx alpha p over dx beta p minus 1. And so just to sketch out a few terms here, let's just say this is two-dimensional. So we would have dx, oh my gosh, I don't know why this software lags so much. dxp over dx1 q, and then this would be dxp1 over dx2q. This would be dx2p over dx1q, and this would be dx2p over dx2q. So essentially the row determines the coefficient of xp, and then the column determines the coefficient of xq. So let's look at JPP. This is going to be, and by the way, so JAB, this would be J alpha B, or J alpha beta is going to be this term here. So jpp is going to be the derivative of xpp with respect to xpp minus 1. And we showed that xpp is equal to p minus 1. We showed that this is equal to negative 1 over xpp minus 1. The derivative of this is just 1 over xpp minus 1 squared. Now let q be different than p. jqqq is going to be the derivative of xpq with respect to xqp minus 1. We showed that xqp is negative xqp minus 1 over xpp minus 1, and so the derivative of this will be negative 1 over xpp minus 1. So these are the diagonal terms of the Jacobian. Now let's look at the row p and the column p. So for the row p, the terms jpq, this is going to be the derivative with respect of xqp minus 1, and then it's going to be xpp, which is negative 1 over xpp minus 1, and that's going to be 0. If we look at the p column, however, this is going to be the derivative with respect to p minus 1 of xqp, which is negative xqp minus 1 over xpp minus 1. And so the derivative of this is going to be xqp minus 1 over xpp minus 1 squared. But we don't really need this term. We'll show that it sort of goes away in our calculation. Finally, if we have p not equal to q not equal to r, then jqr is going to be the derivative with respect to xrp minus 1 of xqp, which is negative xqp minus 1 over xpp minus 1. And clearly this is just 0, since all these variables are different. So now what we have is a general structure for this matrix, right? Essentially, say we have row p here, row p here, row p, and column p here. We know that we have diagonal terms. We know what the diagonal terms are. We know that row p is going to be a bunch of zeros except for the diagonal. And then the column has some non-zero terms. So if we consider a cofactor expansion along this row, essentially what we'll have is this term times the determinant of the matrix formed by, and everything else here is 0 except for the diagonals. So if we get rid of this column and this row, the determinant of the resulting matrix is just the product of these diagonal terms. And so from this cofactor expansion, so we do a cofactor expansion, and again, what allows us to only look at this term is the fact that this row has all zeros except for this term. So we're multiplying this term by the determinant of the matrix that we get from removing this column in this row. And technically we would multiply by a factor of negative 1 to the I plus j, where I and j are the indices. But since we're on a diagonal, I is equal to j, so this is negative 1 to the 2i, which is 1 to the I, which is 1. So that works out in our favor. So now what we have is that the determinant of the Jacobian is the product of all the diagonal terms. Well, the diagonal terms, one of them is 1 over xp p minus 1 squared, and then all the other ones are negative 1 over xp p minus 1. Well, how many of those do we have? We have n minus 1 of those. But now remember, we chose n to be odd. This means that n minus 1 is even, so we can get rid of this negative 1. And now we have this term, 1 over xp p minus 1 to the n plus 1. And since this is even, n plus 1 is even, this term is always positive. So what we've shown is that if we have this intersection, up minus 1 intersect up, the transformation from one coordinate system to the other has a positive Jacobian. And so this applies for all of these charts, or all of these overlaps. And so if we want to look at UP intersect UQ, well, since we have essentially, this should be n here. These should be n's. If we want to get from one number to the other, well, we just can go in steps, right? If we were at 0 and we wanted to go to 2, we could go from 0 to 1 and then 1 to 2. Every time we travel, right, essentially, we're the composition, so composition of implies multiplication of determinants. But since the determinants are positive, if we multiply two positive numbers, we get another positive number. Similarly, if we wanted to go backwards, that's an inversion, and the inversion of a positive number is positive. So we can get from any chart to another via positive determinant transitions. Therefore, odd dimensional projective spaces are orientable. So like I said, this proof is very nasty. It's really just a bunch of symbols. And there may be a nicer proof, but this is how I did it. And it really gets your hands dirty and gives you practice with transition functions and stuff like that. So anyway, I hope you enjoyed this video, and I hope to see you in the next one.